In this video, I want to look at how to get to actual solutions of second order equations when the characteristic equation for it has complex roots. We know now how to think about what happens with complex roots. Right? If I have complex roots, so my roots are e to the a plus ib and e to the a minus ib, we can still think about these as solutions. And I will then get solutions. Y of t is, say, c1 e to the at cosine of bt plus I sine of bt, and I get a second one that is c2 e to the at cosine of bt minus I sine of bt. Which is wonderful, they're solutions, but there's a problem here. And these solutions are going to be complex valued. If I plug in a number for c1 and c2, I get a complex valued solution. This part here is complex valued, and it's going to cause me issues in trying to write this out. If I want to use this equation to model, say, a mass on a spring, that's not going to be complex valued. Right? Physical problems are going to have real valued solutions. So I somehow need to convert these complex solutions into a real valued solution, because that's what I want to get out of this problem when I'm done for what I'm trying to model. Thankfully, it's not too tricky to do so, because we can take the real and imagined parts to get there. And this works thanks to the following theorem. So if p and q are continuous and real valued functions, this is the important part, these must be real valued, then if I have a complex solution, y of t is u plus iv, I can split and take u and v, and separately those will both solve the equation. And this again comes down to the linearity property of this equation, and the fact that p and q are real. So the idea is basically, with this, if I look at u plus iv double prime plus p of t u plus iv plus q of t times u plus iv equals 0, I can take derivatives, those pass through normally, because I is still a constant, even though it's a complex number, it's still a constant. And this will get me that this reduces to the fact that u double prime plus p of t u prime plus q of t u plus I v double prime plus p of t v prime plus q of t v equals 0. And this will equal 0 as a complex number, which means both the real and imaginary parts must be 0, which means this must be 0 and this must be 0. So u and v both solve the equation as it is. Therefore, I can take my complex equation from before, take the real part, take the imaginary part, and then those two are both solutions, which I can then use to write my general solution. So let's give us for a method here. Assume I have roots a plus bi and a minus bi. That means that I'll take the function f, which I know is a solution, is going to be e to the at cosine of bt plus I sine of bt. This is from the root a plus bi. I could take the other one and it wouldn't make a difference. I just get a minus sign in here. But now I can distribute the e to the at. And what I'm going to do is I'm going to take these two here to be my different solutions. So this will be y1, this will be y2. So I will write a general solution that I will put in quotes for now because I have not verified that yet, as c1 y1 plus c2 y2, or c1 e to the at cosine of bt plus c2 e to the at sine of bt. That's my y of t. And then I can solve to meet initial conditions with c1 and c2. But wait, let's check this part first. Do we really know that's a general solution? That means I need to take these two functions here and compute their Wronskian. So in that case, we have w of t will be y1 of t, y2 prime of t, minus y1 prime of t, y2 of t. So I will get an e to the at cosine of bt times the derivative of the second one, which is a product rule term, and then minus y2, I'll put that one first this time, times the derivative of y1, which is another product rule. And if you look at this, we can see that this cosine sine term pair will exactly cancel with this cosine sine term pair because of the minus sign here in the middle. So what I'll be left with from this is just this times this, and then plus this times this. So I'll get b e to the 2at cosine squared of bt plus b e to the 2at sine squared of bt. But cosine squared plus sine squared is 1, and they have the same thing out front, which means this just evaluates to b e to the 2at. Now, is this function 0? The answer is no, it's not, as long as b is non-zero. So as long as b is not equal to 0, then this actually gives a general solution. I have found two solutions that are different enough because the Wronskian is non-zero, and we're good to go. But we know that b can't be 0. I'll go back to my roots. The roots were a plus bi and a minus bi. If b is 0, I don't have complex roots at all, and I'm in different cases. So I would only be here if b was non-zero, so therefore I know b won't be 0, and so this will give us a general solution every time. So this gives us a method for approaching and solving these second-order equations via this method. If we have complex roots, we can write this guy right here as our general solution, we know it is, and then solve for C1 and C2 to meet the initial conditions for our given problem.